Welcome back from lunch. Now we will hear how quantum machine learning is changing data and artificial intelligence. It is presented by Peter Morgan, who will join us online, and later we can ask some questions, so get ready for that.
Hello, everyone. Maybe you can see me at this position for the first time on this event, a little bit virtual, but we have a special occasion why we are doing like this. We are having our distinguished keynote speaker from UK, London, who unfortunately wasn't being able to join us this year in live, but we are sure that Peter, as a good friend of the conference and a member of our advisory board, will be with us next year, maybe even before the conference in November, hopefully, especially if these corona measurements will let us do this much more live events. Like I said, we are going to have a keynote interview with our guest Peter Morgan, and it's going to be a kind of panel interview, which is going to tell us how quantum machine learning is changing data and AI. In every way, in ecosystem way, in sense of academic way, in sense of how we are doing business. So without further ado, I would like to start with the first question, and I would like maybe to give Peter a chance to present himself to our audience.
Hi, thanks for inviting me. I like to speak virtually. Yeah, it is sad I couldn't make it, but with all the restrictions, it's better that we do it this way. My background is I started off in physics, quantum physics, and I was doing a PhD actually in theoretical particle physics in the US at Massachusetts there, and I left and went into industry, and I basically went into computer networking, and then the last 8 years I have my own consulting company in machine learning and artificial intelligence. About 4 years ago, quantum computing came onto my radar screen, and I realized that I could combine, my love of physics with my IT background. So, I haven't really looked back in the last 4 years in the quantum computing space, although it is very early days. So I still earn money from machine learning as well. Yeah.
Okay, I would like to ask you one question before on the beginning of the interview and on the end of the interview, just to see how if your answer will change. So basically, that question is quantum computing the way how we can achieve artificial general intelligence?
Yeah, that's a great question. It may be a part of the solution. I don't think it will be the whole solution, because the reason I say that, is because our brains are definitely classical. We walk around at room temperature. We exist at room temperature. Quantum phenomenon has to be without sort of interacting with the environment whatsoever. So it needs to be, usually that means it has to be cooled right down. So it actually may be a different type of intelligence, but it won't be like biological intelligence.
This sounds very interesting. Okay, I would like also to ask you, how would you explain a quantum computing for data and AI audience? In terms, what's the difference between regular computing and quantum computing? And maybe in what stage of quantum development we are right now?
Yeah, a couple of great questions. So classical computing is what we're all familiar with. It's kind of hard to explain something that's so ubiquitous, right? We've all grown up with it, and it's, it's in our hands with the iPhone, the Android, we have laptops, classical computing is done using classical transistors, gates, and logic circuits, classical logic, and it obeys the laws of classical physics. And, we've got 100 billion processors on a single, transistors on a single processor today. So they're extremely, the most complex things that humankind has built. Okay, so they're classical, but they're extremely complex. Quantum computing, on the other hand, uses the laws of quantum physics. So they have quantum gates, they have quantum logic, they have quantum, quantum transistors, basically. So these things just behave so differently from a classical gate. or a classical processor, CPU, GPU, there's no comparison at all between them. They just use different laws of physics. Now, the way that quantum computing, the reason that people are interested in quantum computing and making a QPU, for example, is that the laws of quantum physics means to say we can do everything in parallel in something called Hilbert space, which is the space that quantum physics occupies. It's just the way the universe is built from the Big Bang outwards. It came endowed with this Hilbert space, which means things can be done in parallel, which gives it the incredible power. And so we haven't actually built anything that can do anything commercially useful today, Alec, but we can certainly prove that they're doing quantum calculations, and we're up to about 100 qubits. IBM announced a few days ago 127 qubit processor. And so really we needed like millions of qubits. So we're at the very early beginning days of quantum computing, which makes it quite exciting too. It's like the 1950s in classical computing.
That sounds very interesting. So basically what we are saying right now that quantum whatever we can end, engineers, researchers, computers, like developers, basically they are some kind of pioneers, if I understand correctly. Is that right?
Yeah, pioneers. Definitely, it feels like being a pioneer right now, which is a great place to be. Yeah, it really is. Yeah, it must have felt like it did in the 50s with classical computing for sure. Even pre-Intel and Bell Labs making the first transistor, we're kind of at that point right now. Yeah, it's pretty interesting and exciting. But again, no commercial applications just yet. So business people are not getting maybe as excited about it as the scientists, for example.
Okay, so with this being said, I would like to go to maybe, okay, we are talking about a new answer like qubit power, that we need to utilize the full power quantum computing with millions of qubits. In what span do you think that it is realistic to have this million of qubits?
Yeah, so we're scaling up. It's on its own Moore's law. The number of qubits seems to be doubling every year. So we've come from 2 to 4 to 8, 50, now we're at 127. So IBM and Google have actually, and INQ, these quantum computing companies who are building quantum computers, have all produced roadmaps out to 2030, which shows the number of qubits doubling every year. So we are on a Moore's law there. So it doesn't take, it's exponential. So it's not going to take 100 years to get to a million, probably more like 10, 15 years. Now, it's not, the number of qubits isn't the only factor. We need them to be not noisy, and we need them to be well connected to each other. And so these are engineering challenges that need to be overcome. It's not a physics thing, it's more of an engineering challenge. So a lot of work to do to build 1 million qubits for sure, but we're on the road.
Okay, with this being said, I would like to ask you, we started a little bit with, the quantum computing as a whole. Now let's move to quantum machine learning. What is the difference between a quantum machine learning and regular machine learning? Yeah,
so regular machine learning, maybe most of the audience at this conference, data science conference, are familiar with machine learning. So basically what quantum computing, okay, so that's machine learning done on classical computers, CPUs, GPUs, TPUs, for example, ASICs, etc. Now, where quantum comes in with machine learning is you can offload a part of that calculation, almost like a co-processor situation, where you have some of the machine learning calculations done on the CPU or GPU, and the bits that will be sped up using quantum are then passed over to the QPU, the quantum processing unit, and then back again, back and forth iteratively. And so the whole thing won't be done on a QPU. It'll be a co-processor situation. So it'll be like a classical quantum hybrid. So we'll always need classical computing for machine learning.
So basically what you're saying, and that will be the second question, but first, if I understand correctly, and correct me if I'm wrong, when we are talking about quantum machine learning, we are not talking about classical terms, only quantum machine learning. We are talking about the hybrid between machine learning or AI and quantum machine learning.
Yes, absolutely, Alec. Yeah, maybe one day in the far, far distant future, everything will be quantum. Like you sort of need to load quantum data. We haven't got quantum memory yet. That seems like a long, long way out. So basically for this foreseeable future, next 10 to 20 years, it will be a classical quantum hybrid system.
This is an excellent question, and this is something that maybe maybe it's a cool thing to say. So basically, what is the role of quantum machine learning engineer and quantum machine learning researcher? Is there any kind of difference in these roles, or they are still the same? But we think that this.
Yeah, that's a good question, because really it's fundamentally comes back to where we are in the quantum computing development life cycle. And because we're at very early stage, a lot of it is quantum computing research at the moment, and engineering a little bit. So kind of like a 90-10% split. We can see that as we progress and build more powerful processors, say with 1,000 qubits, and start putting them, well, they're on the cloud now, but actually they'll be able to be used for very small commercial applications. We'll need a lot more engineers at that point, Alex. So that will be to actually build the commercial applications. That's the point where we'll need more engineering.
Okay, this sounds very interesting. So basically, just to let's say, before we go to the next question is, so basically right now we are all researchers. Some of our developers. But what we'll need, like very, very fast, is somebody who is going to be engineer, if I understand correctly.
Yeah, it will ramp up quite quickly. Again, it's on that exponential curve at the very beginning. Yes. Yeah.
Okay, being said that, can you give us some examples of where quantum machine learning is already applied? Is there any kind of...
Right. Yeah, that's a great, no, not yet, not in commercial applications. So all of this is kind of test you know, companies. It's not just in the lab and university labs, it's in quantum, it's in companies who are wanting to become quantum ready, like big investment banks, big pharma companies, material science companies. We're thinking GlaxoSmithKline, Bosch, you know, Goldman Sachs. These have all got quantum computing departments with 20 or so researchers and engineers and developers working on these algorithms today, whether that's machine learning, optimization, you know, pharma, material science, simulation. So yeah, quantum machine learning is a part of the whole picture, but there are other elements too, like simulation and optimization, as well as machine learning. But so like I say, there are companies hiring, but I think at this point, you know, you sort of need a PhD in, you know, quantum science or quantum information. It's a little too early for them to be employing just a developer with no quantum knowledge. So we have time to skill up.
Okay, and let's say one personal question for you: in which industry you would like to be part of quantum machine learning project?
Yeah, so I'm
focusing. What is the industry that is most, let's say, compelling to you to try quantum machine learning? You personally.
Yeah. Personally, I'm focused on the simulation aspect. So that's material science, semiconductors, photovoltaic cells. So, you know, directly addressing climate change with, you know, also battery physics. So yeah, I mean, it's a huge, very ambitious sort of project, and we're just starting. But once these quantum computers become bigger, we'll be able to simulate battery physics. We'll be able to simulate semiconductors, and a lot of photovoltaic cells are made out of semiconductors, for example, as well as something called perovskite. Basically, it's simulating nature at the molecular level, which was Feynman said in 1981. We can simulate physics with a quantum computer, and by golly, it looks like a great problem because it doesn't look so easy. And 40 years later, we're just at the very beginning of doing that. So it is exciting.
This sounds very interesting. And basically, what is this important thing to understand, not only for data and AI experts and leaders, but also for software engineers and IT industry as a whole, because in the end, there we can talk about, okay, we will just add unbelievable number of, I don't know, computational power, but in the end, computational like hard disks, processor, they have limitation of physical world. Without developing further quantum realm and the development in the quantum realm, whatever we can call like this, we are we are bounded by the limitation. Right now, I don't know if you heard about that. This project, they are trying to close close the gap between the two semiconductors, but basically and the chips, because it's very hard not to have like electricity when it's closer to some kind of nanometers. But like I said, it can be done. But so like I said, it's limited in one part.
No, that's right. So classical computers, we have to make so many approximations when we try to model a semiconductor or any kind of battery physics or any physics at any kind of molecular dynamics, including drugs, drug discovery, molecular docking. So many because basically we're solving the Schrodinger equation, many-body Schrodinger equation for all of these systems, which are quantum systems. And we cannot do that directly on a classical computer. We're using approximations, so we're so limited. So in that respect, if and when quantum computers come along, we can simulate these systems directly. It'll be no contest. It'll be amazing. Progress will be amazing and fast and swift and meaningful and impactful. We're talking drug discovery, solar panels, batteries. A lot of problems are just waiting. A lot of low-hanging fruit. We're just waiting on the hardware.
Only that's the only that's the most expensive part is all the time. What we are like we are low on. Okay. What I would like to also ask is one part is the future with quantum, because what I'm like personally, and what we are seeing like as a society, that we are witnessing that AI is basically changing the very fabric of our society on every level, and people cannot realize because it's day to day. But when you make comparison, like 5 years ago and now, basically we made a progress that is unmatchable. It's not only like because of the COVID crisis that we needed to adopt the digitalization, etc., but because we have adopted analytics, data science, and AI. So the fair question would be, what changes to the society is quantum bringing?
Yeah, no, I mean, I work in the machine learning area. You know, I still, my day job is in machine learning, and I've totally agree with you about the exponential increase in processing power and data, and just algorithmic advancement, and it's been astonishing. If we see a similar type of progress in quantum computing, we can expect to see as impactful, if not more impactful, advancements to society, for sure. I mentioned, attacking the climate change problem through material science. If we can model all these materials and build more efficient materials, that's huge. If we get a 10% gain, even 100% gain in efficiency in a solar panel, I mean, that's $1 trillion industry, no doubt about it. Maybe more. Same with batteries, with electric cars. I mean, another $1 trillion industry. Semiconductors, another $1 trillion industry. I mean, it's just
so basically what you're saying. The Tesla only need to develop quantum computers so they can be.
So we're definitely waiting on the hardware, Alec. But there are several kind of thrusts. There's ion traps. There's superconducting. There's photonics. There's cold atoms. And there's topological. So we don't really know who's going to win in the end with the hardware. I mean, Microsoft is working on topological. Google are doing, and IBM are doing superconducting. IonQ and Honeywell are doing ion traps. So again, that's quite exciting to wonder, and nobody knows who the eventual winner will be. Maybe there'll be a few winners, different applications for different types of hardware. But it's just going to take a little bit of time, Alex. We just have to be a little bit patient.
Okay, but also I would like to come back also to my question. So basically, once again, what do you think, like for the like a regular person, how much their or her or his life will be impacted by the quantum technology, like 5 or 10 years from now? What is your expectation, basically, from the point of one single person?
Yeah, I would say in 10 years, we're going to start to see a lot. 5 years will still be a little bit R&D phase. These things will live in the cloud. We won't have them in our hands like, the phone. So they'll be at a distance. So it'll be more in the background. We'll notice solar panels, solar cells, solar electricity becoming more prominent and efficient and cheaper. So perhaps the average person like you and I will notice the cost of electricity coming down, a speed up in processor power, better batteries in our electric cars when everybody's buying them, because it is policy now, isn't it, with the climate change conference the other week. Governments are getting serious about moving to all electric cars and moving to solar energy. So that's, I think, where the average person will notice it more, possibly in drug discovery, but we're looking 10 years out. I don't want to get anybody's hopes up. This is going to happen next year. Yeah. It's going to be a little way away.
I know that, and we had a keynote a day before, and it's about Vyacheslav Bonich from Raiffeisen. His talk was basically that they already have implemented in modeling, like together, hybrid model together with AI, of quantum machine learning, so banking. So like I said, I think that some of the things will be, but like you said, the full power of it, like, so the regular person can see that's like, I totally agree, 5 or 10 years. I would like to be 5 years, but you're the expert on this side, this matter. So I need to believe on your word that it's going to take 10 years, but still, it's going to be not only people need to understand, it's not going to be 10 years like just if you not do anything. There is a lot of the road ahead of us. So basically, my question is, are companies ready basically to embrace the quantum machine learning in their daily operation? And if yes or not, what is needed to get into quantum and have, for example, 5 years from now, quantum machine learning departments?
Yeah, well, I encourage people, if they're interested in moving into this field, maybe they're data scientists today, software developers, machine learning engineers, to start learning about quantum physics. If you're very young, going to university, doing an undergraduate or even a graduate degree, physics isn't a bad option today. Before it was computer science, machine learning. Today, there's going to be, because it's quantum computing, there'll still be a computer science element, software engineering element, but there's going to be a little bit of physics as well. So it's a little bit of a hybrid, and it's unclear whether people are going to really be able to join the two together in a single person. Maybe we'll just, it's tough, because normally people love physics or they love computer science, and there's a little bit of there's not a whole bunch of crossover. Quantum physics is quantum physics. Software engineering isn't quantum physics. So can a software engineer, or do they even want to become a physicist? Does a physicist want to become a computer scientist? It's a little bit, we're going to have to wait to see how this plays out, but education is key, Alec.
Okay, and being said that, how do you see a cooperation between academia and the business sector in the quantum field? Because it seems that like big tech companies and their R&D departments are a bit in front of academic circles. Is this can said to be a true statement? And what are your thoughts on this subject? Do you think that it's enough, or it needs to be better? If so, how it can be better?
Yeah, well, we're already starting to see companies like Google and Amazon and Microsoft hiring away from universities. So it's a little bit concerning in a way, but we did see the same thing happening with machine learning. All of the big companies like Google just hired everybody from university, and I've noticed they've sort of gone back to university part-time. So, but initially there'll be this huge brain drain, I think, from university, because it's very limited. There's a few professors, a couple of postdocs, and we need a lot more PhDs and quantum engineering and quantum computing. These degrees didn't exist 5 years ago, so we're at the very beginning. And so I am seeing, if you go to Amazon website and look at quantum computing careers, you will see they're looking for postdoc level people today. They can't hire enough. Same with Google, same with IBM. They just simply cannot get enough people with the right skill set.
This is interesting. What just for our audience that can get a bit better overview, what amount of people we are talking right now to have, like, what amount of people do you think that one Amazon, one Google need to have, like, just to make it with what they would like to have as a progress in the quantum field?
Right. Well, I think IBM's a little further ahead. They probably have the biggest quantum engineering team. But I noticed Google and Amazon have about 100 people now, between 100 and 200. They've scaled up in the last 2 or 3 years. Yeah, to 100, 200. They probably want to double that over the next 2 or 3 years as well, and eventually end up with about 1,000 plus. So it'll ramp up exponentially. So the number of people required will probably always lag the demand as we go forward, because it does take 3 or 4 years to train somebody, to become a good machine learning engineer, a good quantum computing guy or girl. I mean, it does take 4 or 5 years. It doesn't happen overnight. So it's going to be a little bit of a ramp up.
Yeah, and basically, and this is like one of the questions that I want to ask this, because I want to share with our audience that basically what we are saying, that right now in the world there is just a couple of hundred, maybe a couple of thousand at most. Like, I think it's too much to say a couple of thousand of people who are doing quantum machine learning. It's not that much. But
no, maybe the whole quantum computing would be a couple of thousand, but quantum machine learning maybe 200. Yeah,
that's right. And basically what can be a good thing, like basically if you're thinking about doing quantum, it's not that easy like to switch to quantum, because you need to understand quantum mechanics on the first. There's somebody who studied that. I can tell you, people, if you saw Brilliant Minds and you didn't, or some film about Einstein, you didn't understand the something that's written on the backboard, that's really true what is written, and that's quantum mechanics most probably. But what would be your advice to someone who would like to start a quantum career, in terms of like students and in terms of somebody who would like to get a pre-qualification? Or is maybe this advice?
Yeah, well, I think we're seeing physicists already become computational physicists, and in the classical sense. So they'll just be able to become quantum computing. At the end of the day, quantum computing will be just another type of computer in the cloud, co-located in a data center along with the classical computers. Maybe there'll be neuromorphic computing as well. It's just another form of computing, and it's only for a very specific type of problem. Won't solve every problem. Websites will still run on classical computers. So to train to get there, there's two ways of getting there. One is to start with the physics background and move into computer science. The other is to start with the computer science background and learn the quantum. And that might be a little harder, I think, than a physicist to learn computer science. I'm thinking because it's just a very specific skill set. It's just, I mean, I did physics, and I know it's not for everybody. It's a lot of math. Okay, there's a lot of math.
Yeah, that's a good output. That's what I'm talking about. There's a lot of people in data science field who are doing very good because they understand their mathematical basically aperture. What it is to talk about for math is very, very hard. It's very, very on some other level. But okay, my last question before we go to your final remark is, what would be the first problem you would like to see solved with quantum machine learning?
Oh man, the first problem, if
only
it's
one.
Quantum computing,
only one.
If it's quantum computing, I'd say I want to simulate materials and build better solar cells and better semiconductor and better batteries. If it's quantum machine learning, I think, like I said earlier, it's always going to be a hybrid classical quantum situation. So it can be used for simulating material science. It can be used for optimization problems. It can be used for anything that machine learning, classical machine learning, which is basically good at pattern recognition, and it will accelerate that process. So I mean, it's almost any field you can think of that machine learning is already used in. So, you can work in a bank, optimizing portfolios. You can work in a transport company, optimizing traffic routes with quantum machine learning. You can, maybe in medicine, AlphaFold, the DeepMind protein folding. I would love to see them using quantum computing to speed that up as well, as would everybody. So any machine learning problem can be, given a little boost with these quantum computers.
From my point of view, what I would like to see is to try quantum machine learning, and what we'll get in combination with quantum computing, it's simulation of black holes, for example.
That'd be great. That'd be amazing.
I think that there's something that we can learn a lot of it from the very fabric of the universe, and maybe we can get from that question we can move on to the ultimate question of them all: are we alone in this universe? Maybe. Of course. That can be a second thing, like doing after that. Like, I don't know. I'm coming back to the roots of my being astrophysics. So
No, a lot of people would like that. I mean, you might not even, we might not even need machine learning there. I mean, quantum computers are just perfectly made to simulate black holes and the Big Bang, because those are 100% quantum systems. Yeah. So you're so spot on there that, yeah, black holes will be an early application when we make them, for sure.
Yeah, still I think that we need like 10 years, but still in 10
Yeah.
years that we can simulate black hole, people, you cannot understand what we can learn from that. That's something that I think it will change, not very fabric of our society, but very fabric of how we are perceiving life, like basically, and that's something that it will have enormous change, like on everything.
Yeah.
But okay, that's 10 years from now. What I would like to ask you right now, would you like to say anything else to our audience right now as a closing remarks before we can start with the Q&A?
Yeah, sure. No, not really. But if you're interested in quantum computing, don't be put off by the physics. Just you know, there's a lot of computer science in there as well. A lot of algorithmic theory. I mean, there's so many different branches within quantum computing umbrella. There's machine learning, there's algorithmic complexity theory, there's information theory, there's software, there's hardware, you know, there's control systems. So there's a place for everybody. So just dive in. That's what I would say to people. You know, don't be put off by the quantum physics bit. There's a lot of work to be done.
Okay. Peter, thank you so much for this lovely chat. It's always very, very pleasant to talk with you. And right now, what we are going to do, we are going to start with Q&A, and Peter will join us live to answer to your question. Hopefully, there are going to be a lot of questions. Okay.
Sure. Thanks, Alec. Nice to speak to you again.
Hello, everyone. Hello, Peter. So you can see me now live. Okay, so basically the first thing is, do we have any question from the audience? Don't be shy, you can raise your hand. There is yes, no, okay, there's two. Okay, let's go here. I will be the one.
Hi, nice to see you again at this conference, and it's a shame that you couldn't come to do a live presentation even, so it was great still. One of the things I would like to ask for somebody who is devoted to education is how to popularize physics to young generations.
Yeah, that's a good question. So I've been doing a little bit of work on this for various companies. It is all about the education at this point, because, you know, there's this kind of massive ramp up going to be occurring over the next few years. A little bit like we saw with machine learning, right? So, you know, a lot of professors leaving academia to go into industry. We're already seeing that with quantum computing. You know, physics departments becoming a little bit depleted already. But but in terms of educating younger folk or people who want to, you know, move into this area, there are actually companies now creating courses, so you don't have to go back to university. Just like with data science, you know, you can do online courses or 3-month boot camps. They're starting to happen. IBM have got some good training material on their website. If you just Google IBM Qiskit or IBM Quantum, and so similarly with Microsoft. So we're starting to see some of these educational materials appear online. So I would just, you know, start Googling, and over the next couple of years, we'll see more and more of this online information. And also we'll see universities starting to offer undergraduate degrees in quantum information science and quantum engineering, which are degrees that don't actually exist at the moment. So yeah, you know, people are addressing it, but it'll be a little bit of a slow ramp up over the next few years. Yeah.
Thank you, Peter. Just another question. Are you also a bit afraid that humankind might misuse quantum computing?
Yeah, maybe. There's always a safety aspect in any technology, right? Any new technology, you know, nuclear weapons and, you know, machine learning, you know, AI taking over the world. And now, rightly so, people are considering what could possibly go wrong with quantum. So it's a good question to think about. don't stay awake too late at night thinking about it. I think, you know, like any technology, it can be used for good or bad, right? It does have national strategic importance though. So, you know, governments are probably doing stuff behind closed doors that will never see the light of day, really, to be honest. But most of the research has been done at universities and big companies and even startups nowadays. And so, you know, the hope is, you know, people will use AI for good things, and similarly with quantum computing, we'll be using it to simulate new materials and drug discovery, you know, helping us with quantum machine learning, optimization problems. And so those are all good things for humanity. But yeah, there'll be an arms race, you know, China, Russia, the usual suspects, and the West, you know, it's, we can't seem to get over that. So we can expect that. I mean, in some ways it's healthy competition. In other ways, it's kind of annoying because, you know, people start worrying about how, you know, bad actors are going to use it. So, you know, it's one of these perennial problems that will never go away, we'll never get rid of. So we just have to, you know, treat it with the respect that it deserves. Maybe some regulations and legislation we'll see happening. But at the end of the day, you know, there's only so much we can do to limit bad actors.
Okay, do we have any additional question? Okay, I have one question for you. I'm going to put you on the spot here, on the light. So basically, Peter, who will you help us to bring at this stage live next year as a quantum keynote speaker?
Sure, Alex, I'd love to come back to Belgrade. Yeah, I mean, I really enjoyed it last year, so sure.
You and who else? From which company? Google or something like that?
Yeah, I mean, we'll try and get everybody from the big guys and the startups as well, who are doing really super interesting stuff. So, you know, the usual suspects would be Google, Microsoft, and IBM, and even Amazon have a quantum computing research department now. So they're actually making hardware, not just putting other companies' quantum computers on the cloud, which you can go and log into now. It's called Amazon Braket. B-R-A-K-E-T, and you can log into about 3 different vendors today if you wanted to. So we could get them along. So that's 4, and then we could get maybe 4 startups.
Okay, thanks a lot. Okay, basically, if you don't have any additional questions, I would like Peter once again to thank you. Like Tatiana said, I'm looking forward to see you again here in Belgrade Live when Corona, hopefully next year, will give us a little bit of slack. We are moving forward with the program. I think that we are having like a small break or something like that, but I will let Zoran, he know better than me.
It's okay. People like to watch you. We have like 5 minutes before we are joined by Simon Boyden, who is going to follow with his presentation. It's going to be a very interesting one about Wimbledon Tennis Championship. So be sure to be here in 5 minutes because we are starting at sharp time because he's joining us virtually.
Thank you.